Good day, everyone. My name is Junming, and I'm pleased to present our latest research finding conducted with my team. Today, we will explore a concerning scenario where your laptop, smartphone, or even your gaming console could be transformed into a tracking device without your awareness. Our research has uncovered a method to achieve this through Apple's Find My network, the system widely used to locate lost iPhones and AirTags. We identify a security vulnerability that allows hackers to exploit the system to track nearly any Bluetooth-enabled devices, not just from Apple. We have named this attack nRootTag. Let's start today's discussion by examining the most commonly used tracking techniques. IP location tracking has been a fundamental part of web technology for decades. Many websites can estimate a user's location using their IP address, but these estimations typically only provide regional accuracy. The precision becomes even more limited when users are connected through network address translation, or NAT. Here is how it gets particularly challenging. In large organizations, like university and corporate offices, hundreds, even thousands of users often share just a small pool of external IP addresses. Users who may be spread across different buildings or locations through a city or appear to originate from the same IP address. When this happens, it becomes virtually impossible to determine their precise physical locations. This fundamental limitation is exactly why IP-based geolocation simply isn't suitable for applications that require street-level accuracy. Wi-Fi-based location tracking has emerged as a much more effective solution. The way this works is fascinating. Tech giants like Apple and Google maintain massive databases that continuously collect and map the unique identifier of wireless access points. If you want to see how extensive this mapping effort is, you can check out the platform like Wiggle.net. They show their coverage is genuinely impressive. But here is where things get complicated. This tracking method faces some serious challenges that are only getting worse over time. The biggest issue is that entire system depend on having a pre-existing database of access point locations. So if you are in an area without any Wi-Fi coverage, or somewhere that just haven't been mapped yet, you are essentially in a blind spot. The tracking just not work. There's another problem becoming increasingly significant: address randomization. This technology, which started with devices address and is now extending to access point identifiers themselves. What it means is that existing mapping become obsolete much faster, and tracking accuracy drops significantly as a result. This brings us to core source tracking, and this is what we really dive into today. So what's core sourcing? It's all about lots of people to work together and create something valuable. Think of it as we help each other out. When you contribute, everyone benefits, including you. And this idea has completely changed how we track devices. You have probably used systems like Apple Find My Network, Samsung Find My Mobile, or Google Find My Device. And here's how they work. Your phone helps to locate other people's lost device. And in return, other people's phone will help to locate yours lost device. The more people who participate, the better it works for everyone. More devices in the network means better coverage and more accurate tracking across the board. Previous research, including OpenHaystack, have provided comprehensive insights about Find My offline finding mechanism. And here is how the system functions in action. Assume you already have an iPhone and recently purchased an AirTag. The AirTag needs to be activated and paired with your account. The pairing process exchanges cryptography material between iPhone and AirTag via Bluetooth Low Energy. If AirTag lost its connection with paired iPhone, it enters lost mode and begins broadcasting Bluetooth Low Energy advertisements. These advertisements are unidirectional, meant to be picked up by any other Apple devices. Apple devices that receive these advertisements collect their current location, generate encrypted location reports, and upload them to Apple's server. Lastly, the AirTag owner can download the location report from Apple's server, using the private key to finish the key exchange process and decrypt the location reports. Location is always a privacy issue, and this is particularly true to Apple when it branding with privacy protection. Any issue will amplify and compromise their reputation. In order to ensure the location report is so exclusive to the owner, they employ end-to-end encryption. Therefore, Apple can claim they do not have access to the location report and they do not have liability. While the idea is straightforward, it is quite a challenge to implement due to the Bluetooth specification limiting the advertisement payload to 31 bytes, which is insufficient for using a curve used by Bitcoin. Apple had to find an alternative solution, and they chose NIST P224. The public key associated with this curve occupies 28 bytes. When combined with fields like company ID and other required fields, the payload is greater than the capacity. To cope with this tight limit, Apple borrows extra space from the BLE address field to store a portion of the public key. The public key is then split into two portions, a portion stored in the MAC address. The other portion is stored in the payload. Classic Bluetooth MAC address has two parts, a leading 3 bytes that identify the manufacturer, managed by IEEE, and the tailing 3 bytes assigned by the manufacturer. This permanent MAC address makes the classic Bluetooth vulnerable to tracking. Bluetooth Low Energy aims to address this issue by introducing randomly generated device address. As shown here, they are non-resolvable private address (NRPA), resolvable private address (RPA), and random static address. Each type has a distinguished bit pattern in the leading MSB position. Prior research, including OpenHaystack and Apple's specification from Internet, indicating the 5-mile network used a static address. We would like to emphasize that only the permanent device address or the public address can be used to identify the vendor. OpenHaystack represents a groundbreaking research that reverse engineered Apple's 5-mile network, demonstrating how this powerful infrastructure can be accessed by independent developers without paying Apple for certification. Their project has gained significant attention on GitHub. While OpenHaystack functions effectively as a proof of concept, it's important to note that its primary purpose is educational and experimental, not intended to use in remote attack scenarios. We find this is particularly true due to the hardware selection and physical access constraint. The story starts when we try to replicate OpenHaystack. We use a script provided by OpenHaystack and configure the public address. When we run this script on Raspberry Pi, we observe the address is changed to match the public key. For example, when the public key is starting with Debbie1234, we expect to see the address changed accordingly. Obviously, the experiment runs without any issue. Their script has successfully sent out advertisements and picked up by surrounding Apple devices. We download the location reports and located the Raspberry Pi. Next step, we try to port their script to run on other platforms. However, when we run this script with a USB dongle or running on another PC, we notice the address will never be changed. And this is an unexpected behavior. If the address does not change, surrounding iPhone will pick up a wrong public key. And because we do not have a corresponding private key, we are unable to decrypt the location report and locate the device. So we investigate further. We have reviewed their source code and noticed something. In their Python script, we find a line that's very interesting. It uses a command that's not defined in the official Bluetooth specification that is used to change the address of the device. We have noticed another issue, a parameter used to configure the advertisement. As pointed out that address type used to send out this advertisement is actually public address. But in the earlier, we have mentioned that Apple specified to use the random static address. So there is a mismatch, and we wonder what's going on. We would like to give an example which eventually lead to the root cause of the confusion. We previously mentioned that by observing the leading two most significant bits of the first byte of the MAC address, we can determine what address type is the given address. Looking at this example, we observe that leading bits are 1, 1. That suggests this address is a random static address. However, Wireshark told us this address actually belongs to expressive intercorporate. This address is being marked for two address types, And which one is correct? Is Wireshark making a mistake, or is us? Turns out, both answers could be right and wrong. We have previously demonstrated a table, including 4 types of address. However, that version is not correct. There is actually an additional bit used to identify either it's a public address or it's a random address. The address can only be determined when we have looked at this bit first. When it's 0, indicating it's a public address or the permanent address of the device. When it's 1, indicating it's a randomly generated device address and it does not have any manufacturer information. Now our confusion is cleared and we have some very important observation that Find network actually accept more address types than it designed. Apple, OpenHaystack, and derived works all made this very important discovery. We have another observation that on different operating systems, like Linux, Android, and Windows, they all allowing unprivileged application to send out Bluetooth advertisements. Linux somehow is actually using public address, and this is why OpenHaystack, by changing public address, can have the advertisements sent out. Recall Apple's design where a private key is split into 2 parts, one used for MAC address, and another stored in the payload. Our core idea now comes into play. If we could find a private key that corresponds a public key that matches the MAC address, we could then track the device. Next, we start discussing how we launch our tag on Linux. Then we further extend the discussion. We address devices like Android and Windows, as their scenarios are more complicated. We have investigated 12 popular Linux distributions. They are all using BlueZ as their default Bluetooth stack, and BlueZ providing an API through dbus, allowing unprivileged application to send out advertisements with public address. Previously, we have mentioned that the public address is actually the device address, and they are managed by IEEE. There are a limited amount of the OUI, therefore we can compute private keys for those MAC addresses in advance and save them into a rainbow table. According to our estimation, to store the entire rainbow table for all known OUI are only costing 20 terabytes, equivalent to a $500 hard drive. Android and Windows use random device prevents MAC address-based tracking. They add another layer of protection by preventing applications from reading or setting the advertising address. Without root access, applications can only prepare advertisement content while the system controls the actual broadcasting address. We discovered an interesting workaround. While an application cannot directly query its own BLE address from the system, it can read other devices' address from their advertisements. This means when there are 2 or more vulnerable devices within a range, they can help each other to identify their mutual BLE addresses. One of our research objectives is to demonstrate that this attack is practical and affordable. To achieve this, we evaluate multiple factors. First, we consider the cost of finding the first match. While constructing a rainbow table allows for immediate response, it requires time and additional cost to store the data. Notably, the demand for this attack can be only a few times. We find that renting cloud GPU is more cost-effective than purchasing them for this attack. For instance, an RTX 3080 costs just 22 cents per hour to rent, with an excellent rent-to-KPS ratio. In comparison, high-end GPUs like the H100 are much less cost-efficient. By using 200 RTX 3080 GPUs, we project a 90% probability of finding a matching key in just 2.76 minutes, costing only $2.2 US. In real-world tracking scenarios, we measure the time between sending the first lost message and receiving the location reports. In a university campus setting, the average latency was under 7 minutes, while in a residential area, it slightly increased to 8 minutes. Both well within practical limits for effective tracking, and they have performed just like the ordinary AirTag. We have also measured the accuracy of the system. On average, the estimated location is within 10 feet from the ground truth. We have also found that the tracking system works effectively even when the aircraft is flying thousands of feet above ground. By comparing the ground truth flight trajectory with the tracking trajectory, we observe an accuracy of approximately 200 feet. This accuracy is sufficient for projecting the flight path and other flight-related information. Our research has been acknowledged by Apple, and they have released corresponding patches. However, we speculate this vulnerability will take years to eventually fade out due to the users are not always upgrading their systems.